Welcome. This talk I'm going to introduce force-free equilibria. So these are equilibria where J cross P is equal to 0. So there's no pressure force, there's no Lorentz force, there are no forces, and it's just in a relaxed state. This might seem a slightly strange thing to be interested in, because particularly in fusion the whole point is to get a high pressure plasma. But it has many applications, partly because it's a useful approximation, because in many cases the plasma pressure is a small part of the compared to the magnetic pressure, and so to a good approximation we can sometimes assume that the plasma pressure is 0. And then there are cases in astrophysics, for example, where the fields can relax because they're in space, and so then you end up with situations where you have force-free equilibria, or very close to force-free. And so it's a useful approximation. It gives some useful insight into different configurations. And one in particular is the reverse field pinch, or RFP, which is historically quite an important device used for fusion research. Okay, so I'm going to go through some of the results you get here. So assuming J cross B is equal to 0, so the equations we're going to use are this: so J cross B 0, and then we have that mu naught J is curl of B. So immediately we just write down that we have the curl of B from this J crossed with B equals 0. And this means that this curl of B must be proportional to B in order for this to be 0. And so we have that curl of B is some constant, I'm going to call it alpha, times B. Now in general, alpha can be some function of space, so alpha is some function of space here, and in principle of time as well. So here we have the first result. So force-free fields obey this law, so we have a curl of B is equal to some proportional to B itself. And this kind of field is called a Beltrami field. So we can get a little more insight into what this alpha can be by taking the divergence of this equation. So we work out divergence of curl of B, and that of course must be 0 identically, and that's equal to the divergence of alpha B. And so we just split this up into pieces. So we have, this is alpha times divergence of B plus B dot grad alpha. And so of course the left hand side is equal to 0, divergence of B is 0, and so this must also be 0. And this means that alpha must be constant in the direction along B. So this is the gradient in the direction of B of alpha is constant here. And so alpha is constant along magnetic fields. Now it can be shown that this is actually the minimum energy state if you conserve magnetic helicity. So there's a concept will come up later when we look at relaxation of plasmas, but this case is where you have helicity essentially is the twistedness of the plasma, or if you have different rings of plasma interlocked, it gives some measure of the topology of the plasma. And so I'll just put the words here, you can look them up if you're interested in more. But this force-free equilibrium, so it's the lowest energy state subject to a constraint on magnetic helicity, which is some kind of measure of the twistedness of the magnetic field. And if you're interested in looking this up, this theorem is called Volta's theorem. Okay, so now we have some constraints. So we have the curl of B is proportional to B. We have a constraint on what this alpha constant must be. We can manipulate this a bit further to get some useful results. So we can take curl of this equation. So we do curl of B is just curl of this alpha times B. And so this part here we just write as this gradient of divergence of B minus del squared B. It's this curl of curl, so it's just vector identity. And now this part here, this just gives us an alpha times curl of B, then plus here we get a grad alpha crossed with B. Okay, now curl of B, this is just alpha times B, So here we get an alpha squared. This again, divergence b is 0. And so we write this as an equation for b. So you write that del squared b plus alpha squared b, and then plus grad alpha cross b equals 0. So that's another way of writing an equation for b. In some cases this is easier to solve than the original we had. So one particularly useful example is, so this is relevant to particularly for fusion applications, so there's the reverse field pinch. So if we set alpha is equal to constant, so that this term here, gradient alpha, disappears, and we look for solutions in a cylinder, so we look for solutions in a cylindrical plasma, where we have a z direction down the axis, we have an angle theta around the cylinder, and we have a radius outwards. So it's a coordinate system r theta z. And so in a tokamak or a toroidal machine, z will become the toroidal angle, but for now we assume this is an infinitely long cylinder. We assume that everything is symmetric in angle and symmetric in z. So all d by d thetas and all d by d z's go to 0. So that the magnetic field is just a function of r, and that's it. So no theta or z dependence. And so we have a b magnetic field which is in theta, so we have a b theta, and we have a bz. So down here, so we have some kind of twisting magnetic field which runs around the machine. So we might have field lines which kind of run sort of around the machine like this. So it goes around. But we have that br is equal to 0. So there's no magnetic field in the radial direction. It's just purely down the cylinder. Okay, so let's work out the different components. So essentially work out the theta and the z components of this equation up here. So without this last term, because we're assuming alpha is constant. And so we have the vector Laplacian, which gives a whole bunch of other terms. So we have for the theta component, so that's from the vector Laplacian, ignoring all terms in theta and z. Then we have the term from the alpha squared term, then that's equal to 0. And so we just multiply through by r squared. We have just changed the partial derivatives into full derivatives because b theta is only a function of r. So these just be full derivatives here. So this is one form of Bessel's equation. And so the solution is just that b theta is some constant b theta naught times the Bessel function of the first kind. So it's being some function of alpha times r, because there's constant in here. So then taking the z component, here we have the terms from the vector Laplacian. So these are from the vector Laplacian term, and then plus the alpha squared term, so bz equals 0. And again rearranging, so we end up with and recognizing that bz is also only a function of r. And so this is also a Bessel's equation with a solution which is a Bessel function. And so we have that bz is some constant, so bz naught times a Bessel function of the 0th kind, again of alpha r. Okay, now these solutions can be plotted, and I'll show you what they look like. So if here we plot magnetic field. So this is the Bessel function of the first kind. Now bz looks a bit different. So bz comes down like this and reverses direction. So we have bz here So it's r equals 2.4 divided by alpha. So the complete radius where the B field in the z direction, so this is BZ, so it reverses. And so if the wall of the plasma is outside this radius, then we have a situation where the toroidal field in a torus is reversed. And so it starts from going one direction, then you have a location where the toroidal field goes to 0, and then it reverses. And this is what happens in a reverse field pinch, that a toroidal plasma relaxes with a constraint on the helicity, and it ends up with a state which looks like this, where the toroidal field reverses direction. And so if we make a plot of what this looks like, it's an image just taken from the Wikipedia page because it shows what the main features are. So you can see on this diagram here we have the various flux surfaces inside a reverse field pinch. So here the z direction we've been talking about is around the machine. So this is z, which has now become the toroidal angle, and we still have theta running. So theta is still going around here, and we have radius, so r going outwards. And so you have the different surfaces inside the plasma, and as you go outwards in radius, you can see the direction of the field in z reverses. And so there's as you go outwards from the red to the blue, so as you go outwards, you find that there's a location marked here where the field in the toroidal angle, so in z, has gone to 0, and then it reverses direction.